My name is Ritesh Sharma. I am from Akgec Engineering College, Ghaziabad. I am working as an assistant professor in Electrical and Electronics Engineering Department. So, I am taking subject the fundamental of electrical engineering in the first year, and today I am going to discuss the topic the phasor diagram of three-phase induction motor. So, it's three-phase transformer or a single-phase transformer. So, first of all, you can see on the slide it is a equivalent circuit diagram of the single phase transformer. We know that a transformer is a static device which is used to transform the voltage level from primary to secondary side. So to any practical or actual transformer, you can see that we have a primary winding. So we have primary winding having a resistance and a leakage reactance. So this R1 is the primary winding resistance R1. X1 is the primary winding leakage reactance. And if we combine both, we call it the impedance of the primary winding, that is Z1. So Z1 is the impedance of the primary winding. So the E1 and E2 are the induced EMF in the primary and the secondary winding. E1 and E2 are the EMF induced in the primary and secondary winding of the transformer. Similarly, in the secondary side of the transformer, we have R2 and X2. So R2 and X2 are nothing but it is the resistance of the secondary winding and the leakage reactance of the secondary winding of the transformer. So we have a load of ZL. Suppose ZL is the load, we call it the load impedance, the impedance of the load. And V2 is the voltage across the load, we call it the load or the secondary side voltage or the load side voltage. And V1 is the applied voltage, that is the AC voltage. Okay, since the transformer is only work in the ACs. So applied voltage is the AC having the frequency 50 Hertz. Now in the primary side, you can see that we have the component called R0 and X0. These are called, these types are R0 and X0 are called the no load parameter of the primary side. And the current is the no load current which is flowing that. So you can see from this, the primary current consists of the no load current and I2 dash. It is a phasor sum of no load current, and I2 dash is nothing but it is the load component of the primary current. So the I2 dash is called the load component. Load component of primary current. So in the previous some lectures of the transformer, we have seen that the operation of the transformer on load. So this terms comes from there. So I2 dash. So when the transformer is loaded, the I2 dash is the counter part of the I2 is there, which is the part of the primary current. And we have this two current, we call it the magnetizing component and the core loss component. The magnetizing component I mu here, this current I mu is a magnetizing current which is basically used to magnetize the core, or which is used for the production of the flux in the core. Whereas the working component or core loss component is basically for the core loss in the transformer. These are the two components of the no load current. So no load current consists of the core loss component IC, or you can write here IW. It's same things. I can write it like this. Working component, and I mu, which is the magnetizing component. So these are the this. So this is the no load current, and the no load current, you can see that the primary current consists of these two current. Now let us this is the simple equivalent circuit of the single phase transformer. Now let us draw the phasor diagram of this. So from this transformer we have to draw the phasor diagram. So first of all, it is required to write the equation. Write the primary side equation and the secondary side voltage equations. So first of all, these are the some known equations which I discussed earlier. Write R1, R2, X1, S2, I naught, I mu and IW. So this is the sum that we have used in our circuit diagram. Now next is our the phasor diagram. So first of all, the phasor diagram So phasor diagram can be drawn for three different load, maybe resistive, inductive and capacitive. So let us first we draw the for inductive load, the phasor diagram for inductive. If the load is inductive, suppose that if the load is inductive, for inductive load, so here in that case this load impedance will be inductive. So inductive. So before that we need to write the voltage equation of the primary and secondary side. So suppose if we write the voltage equation of the secondary side, so that will be equal to your the V2 or this V2, that is the voltage of the load side. This V2 will be equal to E2 minus this drop in the this resistance and decay reactance. So you can write it like this. So V2 will be equal to, or in the other way you can also write it like this E2, that is the induced EMF in the secondary winding, will be equal to V2 plus the drop in the secondary winding, that is I2 into R2 plus JX2. So this is the phasor sum of this. So E2, you can see from this equation, this E2 will be equal to voltage at the load side, which is V2, plus this drop in the secondary side or the secondary winding of the transformer. Now in the primary side, if we see, we are applying the voltage V1, and then E1 is the voltage induced in the primary winding. So V1 should be equal to E1 plus the drop in the primary winding. So you can write down this equation also. So V1 is equal to E1 plus I1 R1 plus JX1. But here it will be minus E1 because the E1 and V1 are opposite in polarity, as we know that. Because this is an induced EMF, and according to Lenz's law, the polarity of this induced EMF E1 will be opposite to that of the applied voltage. So we can write down this minus E1. So again, this is the, so we have these two equations. One is from the secondary side of the transformer and one is from the primary side of the transformer. We can also say that it is the EMF equation or the voltage equation in primary side and secondary side of the transformer. Now to analyze or to investigate the phasor diagram for different loading, we have to use these equations. Okay, we are required to use these equations. So first of all, now with the help of these two equations, we will draw the phasor diagram of the transformer. So first we take the inductive load. So before taking before this inductive load, we know that the voltage, you can see the flux. Sorry, the flux is taken to be a reference, because the flux, we know that the flux is going like this. So flux is given by phi is equal to phi m sine omega t. It means the phasor of flux is almost zero. So we have taken this flux as a reference. Now, and also we know that the induced EMF E1 and E2 will lag the this flux by 90 degree. So E1 and E2, this is the E1, and suppose that this is the E2. This is my E1 and E2, and this is the angle at 90 degree. So we know that the angle between the flux and the voltage induced is 90 degree, because the induced EMF is shown that it is lagged by 90 degree. Now we will first apply this secondary side equation. So E2 will be equal to, now is equal to V2 plus I2, and this drop basically consists of two. So first we can write it like this. This drop, so suppose that the voltage is there, because if we have taken that the load is inductive, so in the load is inductive, the current always lag the voltage. The current always lag behind the voltage. Suppose that we have taken the, this voltage, this is the voltage V2, and the current will lag this voltage, by some angle, because since it is an inductive. So suppose that the current will be taken like this. This is my current, or I2. So there will be some angle between this I2 and V2. We call the power factor between these two voltage current. So this is the phi, or phi 2. So you can say that I2 is a current and V2 is a voltage across the load, or the current going through the load. The next job is to find the voltage drop, this I2 into R2 and J. So you can write this E2 will be equal to from, so E2 this E2 will be equal to V2 plus I2 into R2 I2 R2 plus J I2 X2. Means this E2 must be equal to V2 plus the phasor addition of I2 R2. Now this I2 R2 is a drop, is a resistive drop, and the resistive drop is always in the phase of the current. So this resistive drop will be in the phase of the current. It means that this will be added in this voltage V2 I2 R2, which is in phase with the current. So you can say that, you can write down this or draw I2 R2. And this I2 R2 phasor will be in the phase of this current. You can say these two phasors will be parallel. Next is the JI2 X2. So JI2 X2 means it is the reactive or drop which is 90 degree ahead of the current. So 90 degree ahead, you can say like this, 90 degree. And if you extend this, this will be the E2. This will be the E2. Exact. This is the E2 you can see over here. So this phasor, you can say this E2, that is the E2 phasor will be equal to V2 plus I2 drop. So I2 drop, this drop which is drop, and this Ji2 into X2. So this is our Ji2 X2. And if you draw this, this is for I2 Z2. So this is the I2 Z2 drop. So this triangle which you can see inside this triangle is nothing but it's a voltage triangle, as we have seen in the previous classes. Is a voltage triangle. So this is the phasor diagram for this equation or the secondary side of the transformer. Now next is the primary side of the transformer. Now this is the primary equation. The E2 is already done. Now V1 is equal to minus E1 plus I1 drop in the primary winding. So let us first, we need to draw the opposite E1. So E1 is this, then it is equal to minus of E1. So opposite of E1 is minus E1. So this is the minus E1. Now I2 this, so I2 dash, this is our I2 dash, opposite current of this. This is the, we call it the load component of the primary current, which is the phase opposite to that of the I2. And we have the I0, the no load current, and the no load current is like this. This is the no load current. So primary current, as we know that the primary current I1 is given by I0 plus I2 dash. It is a phasor sum of I0 and I2 dash. So I0 and I2 dash. So it can be drawn like I1, I0. So this is the primary current I1. So the phasor sum of I0 and I2 dash, you can write it I1 is equal to I0 plus I2 dash I1. Now we can calculate the drops. To find a drop, the V1 is equal to minus E1 plus I1 R1. So we can write it over here. So V1 will be equal to minus E1 plus I1 R1 plus J I1 X1. So all these are the phasor. So V1 should be equal to minus E1 plus I1 R1. So that vector is in the phase with this current I1. That drop is a voltage drop. That should be in the phase of this current. So we can draw it like this. This is a I1 R1. The next is I1 X1. So this is the vector which will be 90 degrees of this 90 degree, that is I1 X1, and you can join the initial point and the final point. So that will be your final voltage V1. That is V1. So V1 will be equal to minus E1 plus this drop and then plus this drop. So now again, if you draw this the triangle primary side, I'm just highlighting this with this different color. So this triangle is the voltage triangle, and this is nothing but I1 Z1 drop. Okay, I1 Z1 drop. So in totality, you can say that this is the phasor diagram of the single phase transformer for inductive load, in which the current will lag the voltage by some angle. Okay, it depends upon the load, actually inductive load. So that's why I2 is lagging behind this voltage by some angle phi 2, and the power factor is almost cos phi 2. You can say the power factor of this particular load. So this is for the inductive load. Now let us draw this for the capacitive load. If we draw this the same phasor diagram for capacitive load, for capacitive load So the voltage equation will be same. The voltage equation will be same like this: E2 equal to V2 plus I2R2 plus J I2X2, and V1 will be equal to minus E1 plus I1 R1 plus J I1 X1. These are the two voltage equations. But the only difference is that the load is capacitive, in which the current leads the voltage by angle. So let us draw it again. So first we take the flux, which is the, you know that the flux is taken as a reference. This is the E1 induced EMF in the primary winding, and as we know that the voltage is this is the voltage V2, and suppose this is the current I2, and here you can see that the current leads the voltage by some angle. So let us separate. This is the at the instant where the voltage and the current are on the phasor diagram. This is the minus E1, minus E1. Now first we will calculate this E2. So for E2 is equal to V2 plus I2 into R2. So I2 into R2, this is the I2. So I2 R2 will be in phase with this I2. Let us take another current's color. That will be like this. So this is I2 R2. That is the drop in the resistive branch. Then Ji2X2. So Ji2X2 again, the 90 degree ahead. So 90 degree ahead will be like this. This is 90 degree. 90 degree. So Ji2X2. And if you extend this, that will be the E2. So this is the E2. Voltage induced in the secondary side of the transformer. And if you connect it like this, this is the I2 Z2, and this triangle will be your is a voltage triangle in the secondary side of the transformer. So this is the V2. E2 will be equal to V2 plus I2 R2 drop plus J I2 drop. So this is the phasor diagram for secondary side of the transformer. Now for the primary side, we know that this is the we need V1, that is equal to minus E1, and drop in this I1 R1 and this I1 X1. So for this I1 R1 we need primary current. So I2 is there, so I2 dash must be Let us take some different color. Suppose this is the I2 dash of this I2 dash, and this is the primary current I naught. So we have to take the of this. So primary current is this I2 and I1. So primary current is this phasor sum of no load component and the load component of the primary current, that is I2 dash. This is the I2 dash. I2 dash. Now we have to this add this I1 R1. So I1 R1 drop. I1 R1 drop. So this I1 R1 drop is this, which is in phase the current. So I1 R1 drop, and I1 X1 drop is 90 degree for this. So J I1 R X1 drop. And if we connect this from here to this, if we connect, we will get the required. The straight line is not there, but it is V1. It is V1. And this is the triangle which I am talking about. We connect this line. This is the triangle, voltage triangle of the primary side. So this is the I1 Z1. This is our V1. So voltage V1 and I1. This is the phi 1. This is the phi 2. So this is the phasor diagram for capacitive load, or when the load is capacitive in nature. Okay, whenever current lead the voltage by voltage by some angle phi. Okay, so you can draw it like this. This is but simply by using these two equations. Now for the resistive load. For resistive load, we know that the current and voltage are in the same phase. So it's quite easy now for resistive load. For purely resistive load. For purely resistive load. For purely resistive load. The equation is same. Let us E2 is equal to V2 plus I2 R2 plus JI2 X2, and V1 is equal to minus E1 plus I1 X R1 plus JI1 X1. The equation will be same. Now if you write for resistive load, this is the flux phi as usual, and it is E1 voltage induced in the primary, which lag the flux by 90 degree. Then we have the voltage and current. The voltage and current will be in the same phase. Suppose this is the voltage V1, sorry V2. So this will be the I2. So we can say voltage and current will be the same phase, or there is no angle between this. So that means it's a purely resistive. The power factor of the load must be unity. And then if we calculate the drop I2 R2, that should be the phase of current. This is the I2 R2. This is our E2. Triangle. This is I2 Z2. Again, in the primary side, in the primary equations, we will write this minus E1, then I2, opposite of I2 is I2 dash. This is I naught. the phasor sum of both will be I1, and then we will calculate the drop in the primary winding by simply by adding this. So this is the I1 R1, that should be in the phase of this current, the drop, and this I1 X1 90 degree with this, and ultimately we can add this from this position, so you will get V1. So V1 will be equal to minus E1 plus this, and now you can connect this. So this is the triangle, voltage triangle in the primary side of this, and this is our I1 Z1. So V1 and I1, this is the phi 1. So angle between the voltage and current in the primary winding. So now you can see that we have drawn, this is for the purely resistive, for pure resistive load. The previous one is the for capacitive load, and then first one is the inductive load. So this phasor diagram is very important for the analysis point of view whenever we need to require the voltage regulations. So it is required for the analysis. So I hope this lecture will help you to understand the concept of phasor diagram, and next time we will discuss about some terms of efficiency and all that. So thank you so much. Jai Hind.